So similar to what we did with row vibrational spectroscopy, we can look at what are the differences in energy that we'll observe. So if we're looking at absorption for most molecules, everything will start in the ground vibrational state because there's just not enough population. The molecules don't have enough energy to get to higher vibrational levels. And so the difference in energy we see will be between this v double prime equals 0 state to some some excited state. Because remember, delta V can be anything. We'll get, multiple different vibrational bands that we'll observe. So our difference in energy is going to be, that the wave number that we observe is going to be the difference in electronic states, which is this TE value from our previous plot. And then we'll have the, plus the difference in vibrational energy plus the difference in rotational energy, where this difference in vibrational energy will be equal to omega E prime times V prime plus a half minus omega E double prime. If we ignore the higher order terms, the inharmonicity, V double prime plus a half. For most absorption, we'll see V double prime equals 0, but if we were looking at emission, then the primes and double primes could be, the V values could be very different. And the rotational energy differences will be B prime J prime times J prime plus 1 minus B double prime J double prime times J double prime plus 1. Again, ignoring centrifugal distortion and anharmonicity here. So if we have sufficient resolution, we can actually observe all three of these happening simultaneously. And I want to show you an example of that. So in my postdoc at Emory University, I studied a diatomic molecule, calcium oxide. We talked about it previously. But I just want you to in this context of talking about all the different types of energy that we can observe, I'm going to switch over to my paper that I published. And this is a spectrum that we observed. And so this is a bit confusing because we have a lot of things happening, right? Because there's multiple sorts of energy involved here. And so what we observed is that we saw different transitions. So X here, this is how we label different electronic states. Maybe I can highlight here. No, it doesn't work. Okay. Anyway, so this X singlet sigma plus, this is a particular electronic state. This is the ground state. That's why it's called X. And that's the notation that's used. And so we're seeing transitions from X to the C state. This is the third highest. So it goes X, A, B, C. It goes, according to the alphabet, to a C singlet sigma plus. And so all of these parts of the spectrum with the green dot on top of them are electronic transitions of this for this particular level. We're also seeing at the same time electronic transitions to two other states. One that's the F state, it's a singlet pi transition, and then a new state that we saw for the first time in this paper that we called 0 plus, because we hadn't identified which specific state it was yet. So then so for each of these, right, so the red daggers, these are all from a particular set of electronic transitions, and the green dots are from a different set of energy levels, electronic energy levels. And the numbers here indicate which vibrational levels we're observing. And this kind of goes to show that delta V equals anything. So most of these are starting from 0, from the V equals 0 state in the X state, and going up to, in this case, going up to V equals 6 in the excited state, or V equals 2 here. And we see 0 to 3, 0 to 7, 0 to 8, 0 to 4, 0 to 9. And occasionally we see things from excited states. So 1 to 6, this is what's known as a hot band. So it started in V equals 1 and then goes up to 6. So we can see that we have very large differences in the vibrational quantum number. So here we're seeing the vibrational part and the electronic part. And if we zoom in on one of these, so if you take the 7-0 band here, we can actually even observe, because this was a high resolution experiment, we can even observe the rotational transitions. And so these are the different J values, and we have R and P branches, just like we did when we observed HCl. The difference here is that the molecule changes in bond length so much that the R branch lines actually turn around and go along with the P branch lines. So they don't spread out in two separate branches. They kind of overlap each other. but we're still able to assign that. And from that, we can find out more about, the bond lengths and what's happening as the molecule gets excited to different excited states. So this is an example of how we can apply, these differences in energy that we're seeing to actual experimental data, that we can observe this sort of thing.